Hello and welcome to this Claritas presentation on the image application and in particular the 5D interpolation algorithm Stitch. As with all of the image applications, the application is available from a dedicated tab on the image launcher. We will initially click on the Scan Edit button and select a suitable input dataset. For this test, I will use a single offset plane. Once I've selected my input dataset, I just click on the Scan button. You'll see the progress meter comes up to show how far we are through the scanning of the dataset. As this is a full offset plane for a 500 square kilometre 3D survey from offshore New Zealand, it'll take a couple of minutes to scan. Once the scan function is completed, you'll see that there is now a warning triangle on the edit button for the prep application. If I now open the parameter form for the prep part of the workflow, you'll see that basically a lot of the fields have been populated. We have a geometry grid that has been set up. From the scanning process. The process requires a velocity field, so if I click on the velocity button, again select recently used and pick up the segue velocity field that's there. You can see that the inline start and ends and crossline start and end have been automatically populated as part of the scan process. To speed up the running of the Stitch and Stitch Prep modules, I will limit these ranges. Now I can use this with the up-down arrows, or I can highlight and type over the relevant values. You can see every time that I go the wipe out the end in line, it then comes up with a warning triangle. It has also extracted from the trace header the minimum and maximum offset range in the dataset. Now I can input shot or CDP gathers into this process as well, hence the fold parameter. So if I was inputting pre-stack gathers, shots or CDPs, then I would define my desired output fold for my CDP. As I've just got a single offset plane, I will set that to 1. The range parameter basically defines how far from the center of the bin I want to search for a trace. And then I can also do some selection parameters so that basically after the prep stage has run, I should only have a single trace per offset CDP bin. And I can make a selection based on, in this case, distance from the bin center is my primary selection criteria, and then I could alternately also add azimuth as a selection criteria as well. Now that the prep stage has been processed, again I can click on the prep run button and run the pre-processing. Again, I get a progress bar up to keep you informed as to how far along the process is. You see this is slightly faster because we've limited the offset, the CDP and inline crossline range that we're going to process. And again, once that process is finished, again you can see that now the Stitch Edit button has a warning triangle because there are parameters that need to be completed by the user before it can run. If I click on the toggle button here, I can open up the logging window and we can see some of the diagnostics that have been sent back to the screen for each of the stages on completion. So if I click on the Stitch Edit button, it requires an output file. So as I had input segue revision 1 data, it will output segue revision 1 as its default. Now I have a choice with this process of either running it locally on the current machine I'm on, or if I've got a larger cluster I want to submit to, I can submit it to a batch queue and allow the batch queue to define where the data gets run, the process gets run. As you can see here, I have batch queues on this machine, so I can run locally or submit to the queue, and the names of the queue are also automatically identified, and if there's more than one I can again select from a list, but I will continue to run locally at the moment. So I can choose the direction of interpolation, so in this case crossline. I can decide whether I want to bin center the data or not. I can define the maximum angle I want to interpolate out to. Some other parameters to control the interpolations, so correlation envelope width and length, number of iterations to iterate around that process, thresholds, extraction iterations and termination thresholds, etc. These are described in the documentation for the application, and I won't go into any detail on them. And then we have the Mpi configuration. So typically Mpi exec is a fairly standard system call, and I can define the number of processes I want to run on, and I'll leave it at 8 at the moment. Typically the default parameters for the interpolation work quite well, so I would suggest certainly on your initial run leaving these as they are and seeing what the result looks like. So once I've parameterized and the warning triangle's gone away from the edit button, I can then click on the stitch run button to run the interpolation. Again, you see we get a progress bar. So first it goes through and sort of checks, confirms the data, and then it starts running the actual application itself. And then the processing is finished. The stitch and stitch prep applications can also be run in standard Claritas job flows. The parameterization is very similar for both of them, so I won't actually open up and show you the job flows themselves. So now we'll move on to looking at some data after stitch, which is basically from our 3D Hawke's Bay survey that we use as a test bed. So we'll transfer over to that one. We will now take a look at some data examples from our 3D survey that we use as a benchmark. First, we'll take a look at crossline 3001. On the left-hand side of the screen, you'll see the crossline after initial processing, including tau-p decon and deswell. And on the right-hand side, you'll see the same crossline after 5-dimensional interpolation. So you can see on the left-hand side, the crossline generally well populated. You can see there's a couple of areas where entire sail lines are missing, and some obviously low fold areas where we have high amplitudes, general striping, spiking. There's bits of areas around the water bottom where traces are missing and fold is low. Then we go across onto the 5D interpolation result. Generally the striping and I guess the acquisition footprints been removed slightly. Less obvious on this dataset, or completely removed in places such as over here. And again, these missing traces up through here have been successfully interpolated. The two areas where full sail lines are missing again have been quite well interpolated. The general trend of the seismic is continued across and interpolated quite well. Typically, as with all interpolation, the data through there looks cleaner because there's less random noise, as interpolation algorithms are quite good at interpolating signal, but less so on the noise. Other things to take note of is that generally the water bottom is better resolved after the 5D interpolation than pre-interpolation, and the data is generally cleaner, better quality. So if I'll now bring up a couple of time slices. So I'll go to time slice at 1250. So that's a time slice after TLP decon and deswell, and then if we get the same time slice after the 5D interpolation. So if I sort of toggle between those two time slices, you can see the benefits of the interpolation. So you can see on there, we've got the missing sail lines. We have some striping and some acquisition footprint that's apparent on this time slice. If I toggle to the new one, you can see that we've interpolated reasonably well the missing sail lines, and the acquisition footprint has been quite well removed where the low fold area, so it's less obvious on the interpolated data set. And the structures look quite well imaged after this process. And you would say that the interpolation algorithm's done quite a good job at filling in where no information was available. So that the structures, particularly round through here in this structure, look to have been resolved quite well and interpolated effectively. And then I'll just take a quick look at an inline before and after. So that's our inline after interpolation, inline before interpolation. The benefits are less apparent in the inline direction, and maybe this is because this inline's was well populated beforehand. But again, the water bottoms better resolved, the data's less noisy, and so is a better input for the migration process. Thank you for taking the time to watch this Global Claritas presentation on our 5D interpolation algorithm Stitch. If you have any questions or would like to take an evaluation of the image suite or the Claritas seismic processing software applications, then please contact us on claritas.sales@gns.cri.nz. If you're an existing Claritas user and require some support with the use of Stitch and other algorithms within Claritas, please contact claritas.support@gns.cri.nz.